let's talk about convolutional neural networks. All right, so we've talked about these in class already, but this is a specialized kind of network that is going to detect patterns. And what that means is it's not examining the data as a whole. So we saw in class that we can perform image detection using a fully connected network or dense network, and that pretty much looks at all the pixels as a whole. So convolutional is going to allow us to just look at specific pieces of it and detect patterns and in some of the smaller parts. So of course we have some challenges with detection with text, specifically these listed over here on the left. Translation means that something is moved, so you can see that on the X it's kind of up here at the top. The X here in the middle is scaled down a little bit. The third one is rotated a little, and of course this last one is using thicker lines. So all of those issues, looking at a pixel by pixel basis, is going to cause potential problems. What we'd like to do is have some sort of network that can generalize. So if we look at this using just straightforward discrete data, obviously it doesn't match pixel by pixel. So of course, convolutional neural network, CNN, is going to focus on matching pieces of an image. And specifically, you can see here that we have a diagonal line on the top left that is kind of like a backslash. Down on the bottom left here, we have what looks kind of like a forward slash. Okay, and in the middle, you can see that we have an X. So right away, we can see that it can possibly address the problem of rotation and translation. So we call these things features. So the features we looked at were a diagonal line going from top left to bottom right, an X in the middle, and then a forward diagonal line. And these are the specific patterns that you see within this X, even if it is rotated a little bit. So you can see the image on the left, and then you can see the specific features on the right here. So as far as a convolutional neural network is concerned, we have to think about what is going to label a network as being convolutional. Well, the first thing is it has something called a convolutional layer. Sometimes people refer to the convolutional layer as both of these things. That's okay. When you code it, they are two separate things. The filter is going to be a layer by itself, and pooling, which is the process of shrinking down an image into less pixels, that is also going to be a separate layer when you code it. So what is the convolutional layer? Well, it's a layer that is looking for specific patterns, such as edges or corners or circles or squares or diagonals. So those are pretty primitive patterns that we're going to be looking for. We're going to see that later on we're going to have some more advanced patterns, and I'll show you that in a couple slides from here. In the next slide, we said that the simple patterns are going to be in the early convolutional layers, such as just the outlining of something, or perhaps the corner of something or a circle or something like that. Then as we traverse deeper into the sequential convolutional layers, we're going to pick up things like fur or eyes or feathers. And then maybe even later on we can classify something like a dog or a person. So what we need to do is talk about the concept of filters. So a convolutional layer has one or more filters, and what that is just a matrix, and we will pick the size for it. And when we want to learn what these filters should be, they will be initialized with random values. However, in the samples, we're going to be looking at kind of some predetermined filters here. So when we look at this network here, we can see the input layers on the left, and we can see that there is a convolutional layer. So again, sometimes people will simply group all the convolutional layers and say that's the convolutional layer, but again, in code, you're going to be making several of those separately. And this is the layer that's going to have some feature extraction in it. Okay, so let's look at the concept of a filter. Okay, so we get the term convolutional because the filter will slide across the entire image, usually only 3 by 3 pixels or some small window at a time. So here we have the MNIST database, and first of all, NIST is the National Institute of Standards and Technology, and this is a database of handwritten numbers. And what we're going to do is demonstrate the concept of convolution and sliding windows. So when we look at this animation here, we're going to just pick one number, and for example, we're looking at a 7, and we can see a close-up of the pixels here. So this green box represents a window that's going to convolve or slide across. So it goes and slides essentially 1 pixel at a time. And as it slides, it pretty much only considers the pixels that are inside the green box. So eventually it's going to make its way across all of the pixels in a 3 by 3 window. So when we look perhaps at this box, we can make an observation that the bottom pixels are not lit up. And when we have such a case, then we would make the assumption that we are looking at a bottom edge, okay, because we have pixels lit up at the top but none at the bottom. And as this slides across, all of these pixels along this bottom edge of the 7 are going to have all of their pixels lit up at the top and none at the bottom. So the green sliding box that you saw was called a filter. We didn't really look at any values inside it. We just showed the concept of sliding it or convolving it. So a filter can be set to detect any sort of pattern, such as a top edge or bottom edge or a left edge or a diagonal line or an X or whatever. And of course, the movement is called convolving. Okay, and an edge is where we're going to have some area of high contrast. So even just looking at this slide right here, this of course would be an edge where we have some high contrast. This line of course might be considered an edge, right, because we have high contrast between the white background and this orange line. So what we do is we actually use a dot product, or just a sum of all the products in a matrix, and it's a pretty easy operation to do. So when we look at this particular example here, we're going to see how we can perform a dot product. And what we would do is we would take this filter. So this is the filter right here with the 0.979 in the top left corner. We would take this filter and apply it over here in this box. And what we're going to do is multiply every single number in the box by each of their respective positions. So we would take 0 times 0.79, we would take 0 times 0.278, etc. And then we would add those all up. Now, of course, up here, since these are all zeros, we would get zeros for all the multiplications, and when you add them up, you would get 0. And then that number goes right here. Okay, so really, until we slide this thing all the way across and then down across, we're not going to get any values until we get into this area. Now, this filter isn't really doing anything special other than maybe just blurring this or smudging it a little bit, which of course, could be an effect, in Photoshop or something like that. But we're not going to see anything over here on the output of this filter until we get down into this area. So you can look at this link if you would like to. If you need to find this video, you can just search for Deep Lizard. That's the author. And specifically Convolutional Neural Networks, CNNs Explained. Once you search for that on YouTube, you'll be able to stumble upon this video that I was referring to. So here we can look at some examples of filters. Now, again, these are just example predetermined filters. We're going to eventually hope that our convolutional layers will learn these by themselves. But to decode this, we have kind of like a reverse image here. So we have light pixels on a black background. Okay, so just keep in mind that black means there's no pixel on, and then white means there is a pixel, and then somewhere in the middle between these two is gray. Okay, so if we consider this filter here, okay, this, you can see that it has -1s on the top, meaning black. It has 1s in the middle, and then some gray there. So if that were the case, we would be looking at a top edge, because a top edge would have no pixels above it. Also, sometimes we have a little bit of blurriness, or anti-aliased pixels going on here as well. So here we can see that we're detecting left and right edges with these, and then filters 1 and 2 are doing top and bottom edges. All right, and this slide, these filters are outlined here. Okay, so we can see each of the edges that it is detecting. So this one is getting a bottom edge, this one here is getting a top edge, and so forth. Okay. So when we look at the filters, and if we were to convolve or slide this filter across all of these pixels, we would get an output layer that looks something like this. Okay, so anywhere where you see bright white would be the areas that are kind of passed through the filter. So this is showing us that we have a top edge detected because we see very bright pixels here on the top. And then we have very dark pixels on the bottom, which would mean pretty much the opposite of a top edge. Okay, so this is very far from a top edge. Okay, and then we have the same things going on with the second, third, and fourth. The second is a left edge. The third is a bottom edge detection, and the fourth is a right edge detection. Again, these are predetermined filters. All right, so let's look at an example of a left edge filter. So here we are looking at an example of a left edge filter, and that would mean that we have pretty much no pixels lit up on the left, followed by some pixels being lit up. So again, this is a 9 here, and we would have no pixels lit up to the left over here, and then a sudden change in contrast like this right here. And what's going to happen when we multiply and add those through, we're going to see the value. The higher the value is, the stronger the case that it is a left edge. So right here we can see a 2.6 and a 2 and a 1.3, and then some over here that are in the 2s, where the right edge would be pretty much the opposite of that, and we can see we have negative values there. So of course the red marks a strong left edge. Right, and of course we could repeat this for the right, top, and bottom. And then if we were to superimpose these, we would get all the edges. Now, I'm not saying that's exactly what a convolutional layer does. I'm just demonstrating what a filter does. So if we were to get all the left edges and top edges and right edges and bottom edges and then just put them on top of each other, we would get all of the edges here. Okay. So you can see what would happen, right? We would just take all of these and essentially get an outline as shown in this example here. Some other edge detection filters. This is more for image processing. But here we have a Sobel filter, which is it's kind of a standard filter. Then we have this Char filter, which really is the same concept here. You can look and we can see that just the ratios between these numbers are different. So here we can see a 2-to-1 ratio, and here we see, you know, like almost a 3-to-1 ratio here, roughly 3-to-1. So that's the only difference between these. Okay, so one of the things we're going to do is be able to apply a filter and get an output value, and eventually we will squash these values down so that we don't have any negative values. So of course we can see that these negative values tell us this is kind of like an anti left edge, but eventually we're going to squash these down and just turn them into 0, and that's what a Rayleigh filter does. All right, so let's look at convolution. We're going to take a feature. such as an early one, such as an edge or an X or a slash. And we are going to try to cross every match. And then we're going to get a map of where each feature matches. So let's take a look at this one. We have 3 different filters, backslash, I'll call that, X, and forward slash. So if we take this filter right here and we go ahead and slide this across, so we would take this filter and slide it across this thing right there, we would see that it kind of matches. So this partial diagonal kind of matches, right? So what we would do, we would just multiply the -1 times the 1 plus the -1 times this 1 times this plus this -1 times this -1, etc. Add them all up, and we're going to get this value right here of 0.77, which is a reasonable match. Okay. Now, when that filter makes it all the way down to, let's say, right here, then we're going to get pretty much a perfect match, because this filter is exactly the same as these pixels that I highlighted. Thus, you can see that we have some perfect matches essentially right here, right, and right there. So any really high value on the right side, or really colored toward white, not black, would be a strong match. So we can see we have a strong match right here, and we have a strong match right there. We don't really have any strong matches anywhere else. We do have some pretty negative matches, right? So for example, if we put this filter and put it over here, that is definitely not a strong match. Now, although one of these matches, the majority of the other important pixels do not match. So we can repeat the same thing. Here we have an X, and when we would start it out over here, we have a very slight match of an X. We have 2 of the pixels matching right there, but these 3 don't. So it's a very slight match with 0.33. And of course, eventually, when this thing makes it all the way to the middle, which would be right here, and when we multiply and add these all up, we would get the most perfect match here, right? And then the value is stored right there in the middle with a 1. And then just repeat that same process for the forward slash here. So this shows you what each of the outputs would look like after we run these filters across this image. Note that we have 3 separate filters. Okay, so there is not really a relationship yet between this output and this output, which may be this green one and pink one. And that's really the difference between a fully connected network and a convolutional network, right? The fully connected network is going to have all of the outputs connected to the next layer's inputs. And in convolutional layers, they don't do that. So the next thing we need to talk about is pooling. And there's a couple reasons why we're going to do pooling. So first of all, the concept of pooling is shrinking down the image, and that's going to help us with translation. And it's also going to help us with some generalizations as well. We're going to do the most simple kind of pooling, and this is called max pulling. And here's the steps that you would perform in max pulling. You want to choose a window size, usually 2 or 3 is typical. You want to choose a stride. Typically, it's going to be the same value as your window. Okay, so you'll see in TensorFlow that is the default value of the stride. If you don't specify it, it's going to be the window size. We're going to move it across the filtered images. Oops. And then from each window, we're going to keep the max value. Okay, so it would look like this. So it looks like our window size is 2. And we consider the pixels inside this highlighted window, and we keep the max. And then we would just put it right there. The next one, we slide over by 2. That was our stride. Consider all the pixels inside there. Keep the max one, that's 0.33, which is right there. And then, of course, continuing that process on, we see that we have kind of a shrunk down version of this thing here. Okay, so we still see this diagonal line here a little bit. We also notice that some of these are kind of filtered out. This very strong negative kind of averages out with these, and we see here that it's filtered out, and we just have 0.33s, 0.55s, and so forth. Okay, 0.11 was in there too. Okay, so if we would max pull all of these, we turn this 7 by 7 image down to a 4 by 4. Okay, and if you do have an odd number, you simply just kind of ignore the edges or treat them as 0. So of course we would have this, right? There's 1. Okay, when we slide it over by our stride, we would have that. When we slide it again, right? Okay, we have this. And then, of course, we're at an oddball one here because we don't really have anything here. So you just consider those pixels, or you just treat these as, a very small value. And of course, that's why we have the 0.33 going right here. All right, so we're going to talk about normalization. We're going to perform normalization a couple different ways. And we're going to use ReLU to change values from negative to 0. Now, these examples I showed you, okay, right here, these have pixel values of 1 to -1. Okay, typically we're going to be working from 0 to 1. Okay, so sometimes we get images that are bytes, 0 to 255, and we have to normalize those down from 0 to 1 with a floating point number. Okay, so that's one way we're going to probably have to normalize. And then another way, of course, is just using ReLU to get rid of the negatives as well. And long story short, it just keeps the math from breaking and us getting very, very large numbers within our network, because we don't want to have like overflow errors or anything like that. Okay, so a sigmoid function, you can have negative values. Okay, so we can see that. With ReLU, of course, we just only have positive. So anything negative just simply turns to 0. So the function is just the max of 0 or the value itself. Okay, so it just puts a floor of 0 on that. So if we were to normalize this, right, this negative 0.11 would simply become 0. right? So the normalized version looks like this. Okay. Now, what about the magic in putting everything together? So the first thing we're going to learn is that when we have convolutional networks, normally we have more than one convolutional layer. Now, within this convolutional layer, we might have many filters. So as shown, you can see that this layer here might have 128 filters. This one might have 128 or more or less filters. This one might have 50 filters. All right, and these filters are going to be learned. So yeah, they will start out with random values inside there. And as stated, the early filters are going to be doing very simple things like detecting edges, and then later on through the network, we're going to extract features like eyes or ears or something like that. Okay, so we would have some convolutional layer, right? And all that is a bunch of filters that are initialized randomly. We run this image through all of these filters. Okay, so if there's 100 filters in this convolutional layer, we have 100 outputs. And then we would maybe run ReLU, right? We might do another round of convolution, another round of normalization, and then we might shrink it down and use max pooling. So this is just showing you an example of how these convolutional layers can be set up. Notice we don't have to have pooling or shrinking each time. It really depends on what your features are. You might have to examine the outputs of these convolutional layers to see if you need to shrink your data space down or not. Really depends on the size of the input images and so forth. But in any case, if we have some inputs, okay, I'm sorry, if we have an input, which would be an image into this network, we're going to eventually get some outputs. Okay, now each of these would be the output of the separate filters from the very, very last layer. And it looks like we have 3 2x2 squares in here. So, what we would do eventually is take this and run that through a fully connected network, or we call it a dense network. Now, as I discussed in the previous slide, the convolutional layer is unique because we don't have connections between those filters. Okay, so when we look at this, the filter from a slash is not connected to the filter with an X or something. Those simply don't get connected until we get to the fully connected layer. So the way this is going to work is we're going to have this thing here as the beginning, okay? And then we're going to be ending up with just these filtered images, right? And what we do is kind of take those filtered images and run those into a fully connected network, and then we can get some outputs here. Now, if we were just trying to determine an X or an O, we would only have 2 outputs here. Okay. All right. So this is showing us kind of picking up from where the convolutional layer stops and the fully connected layer starts. So we see that 0.9, 0.65, and so forth. What we're going to have is just some data values in here. Okay, and we're going to have them unwrapped, or what we call flattened. Okay, so this is just here's the first square right here. Here's the second 2x2, and here's the third one. It's just unwrapped so that we can have each input going into a fully connected network, and then our output layers would be just an X or an O. So we would have 2 on the output. Okay. Now, this example is pretty simple because we're only classifying an X or an O, and that's not very hard to do. We could probably get away with just having straight weights or voting. Would not be very difficult. But in any case, we will go ahead and connect it to a fully connected layer and do more challenging problems. Of course, this is going to be a winner take all. That's pretty easy to do in Python. We'll see that we can just use an argmax and pick whatever one is the highest. So putting it all together, right, we get an image sent into our giant network here. Okay, so we'll have some convolutional layers toward the beginning, some normalization and some pooling. Okay, so eventually at this point we would get an output. So this point here kind of marks where the convolutional layers end and the fully connected layers begin. Right, so this is your normal neural network or deep network, and this of course here is the convolutional layers. Specifically, this is a convolutional layer. Sometimes I just classify the whole thing as the convolutional layer, but in code, like I said, we'll see that you do need to put each of these layers in individually. Okay. The next thing are the hyperparameters, and those are going to be the dials and knobs that we can change when we're talking about tweaking a convolutional network here. So obviously the number of filters, okay, and the size of the features, right? So we're talking about how many convolutional layers, how many filters are in each convolutional layer, and what is the size of each of those filters. Okay. Pooling, we can experiment with the window size and the stride, and then all the things we learned about before with a deep network. These are only a couple parameters, but all of the parameters that we can change inside our fully connected layer have to be considered as well. So previously we looked at doing some image classification of those MNIST handwritten numbers using a fully connected fully connected network, which can be done for small data sizes, but it's not practical for larger ones. We're now going to look at the convolutional neural network implemented in Python and TensorFlow and Keras. I happen to be on a GPU. I'm just going to go ahead and rename this first, and then we'll get rolling here. So this is the convolutional neural network. Okay. So the first thing we're going to want to do is import your normal libraries that we always do. This will take a second. So eventually it does import. So the first time, of course, it takes a while. Then just go ahead and grab your other libraries. So we'll grab some plotting tools, and we'll get NumPy. And of course, make sure it is on code, not like what I did. That looks better. Okay, so the next thing we can do is once again grab the MNIST database. So that is the database of handwritten numbers. All right, so what I'm going to do is go ahead and read in that data into a couple different sets here. So I'm going to have it as train images and labels, test images and labels. Okay. Now, what I'm going to do for this, I'm going to make a copy of this because we need to change the format just a little bit so that we can make it printable here. So I'm going to make a copy of this just called printable train images, and I'm going to make a copy of the testable ones, and you'll see where I'm going to use that later on. And by the way, it's just Shift Enter to run any line you're on. I'm not sure if you know that. You can go ahead and hit the play buttons, but this one's better. All right, so just as a sanity check, we can just maybe print the shape of this. 60,000 looks good. And we can pick some random one. I think I pick, how about, let's just say 50. And this should be a 3, and that kind of looks like a 3, close enough for us, right? So looks like we have the data set okay. All right, so for this, what we need to do is, since we're going to be running into some filters here, we need to change this and unroll it into a one-dimensional array. So we're going to take the train images. Now remember, I already made a copy of this, so I can just print it out, right? I could have just done this with printable test images as well. I mean, that would make sense too. But down here, I'm going to change the shape of it. So I'm going to do train images again, dot reshape, and I'm going to make it 60,000 by 28 by 28 by monochrome. Okay, like that. So what this is doing is, here I'll put a comment, this would be just change the format so each image is flattened into a single dimensional array. Okay. All right, so let's see, we printed the shape up there, 60,000 by 28 by 28. So if we print the shape again, it should be 60,000 by 28 by 28 by 1. All right, so now when we look at this format, we're essentially going to get this thing unwrapped. All right, and we're going to get one more bracket up here at the top. So when I display this, we're going to see this as, let's see, this would be, I think we did train images 50 is the one we did. Okay, so this should be a slightly different shape there. So it's the same data, except we can see we just have them into these groups of 28 here. Okay, and there's some of the data. All right, so that looks okay. All right, so the next thing that we'll do is we'll go ahead and work with the data a little bit more, and we still need to normalize these values so that they are between 0 and 1. So there's a lot of ways to do this. One of the ways to do it is just to divide it by 255. I think I showed you that in the last video. Here, let me do this. Let's mark this down. We'll say we're going to normalize this to a value between 0 and 1. So maybe this time we'll do it like this. We'll say train images equals train images. You can just do as type, and then we'll cast it to a float, float 32. And then we'll divide it by 255.0. Okay, I think actually we wouldn't have to have the 0.0. That would still work, but I like to put the 0.0 in. All right, so now probably what we want to do is maybe do another sanity check and make sure that looks in the correct format. So yeah, we have zeros as a float now. That looks good. And we have numbers here. Okay. Let's see. Does that look right? Okay, so once again, I screwed it up by running this twice. So I took the values, divided it by 255, and then I divided it again. So I need to reset my train images. So just be careful running code more than one time here on certain situations. Okay, so for me, I'm gonna have to go back up here and start back up here and load this data. Okay, so that looks okay. Shape looks okay. That looks good. This shape looks good. All right, so the shape is okay. Now we have to normalize this down. So I apologize for making this bug, but maybe you can learn from this as well. So now I'll divide it by 255, and then when I print it, these look better. They were way too small before. So that's why it's occasionally good to just do these little sanity checks to make sure your data looks good. So this looks a lot better, right? And just to reiterate, I mean, what happened is I ran this again. So if I keep running this again, I'm going to just keep dividing my data by 255 every time, right? And then I get these really, really small numbers, right? So don't do that. I'll go ahead and fix it offline. I'll just run everything and get it back. So I'll just do run all cells. And of course, everything looks good now. All right, so a little learning experience there. Just be careful with. All right, so what we want to do is kind of do the same thing, but for the test images. So really, this is almost a copy and paste, except you want to just go ahead and get your test images into the correct shape and format it like that. If you want, you can go ahead and print this. You don't have to hit print all the time. You can just put the name of a variable if you want like that. So that works too, or you can just, you can print it like that. Either works. When you just do this, you get the data type as well. All right, so we want to go ahead and do a one-hot encode on these. So let's do this. So I'm not printing it there. Okay. So this is marked down. Let me put it like that. Okay. All right. So to make this data a one-hot encode, what we want to do is do this. We just want to do a to categorical on the train labels. Okay. And then we want to do the same thing for the test labels. Whoops. Okay, so if we just take a look at this, we'll see that we have a one-hot encode going on those. All right, now we have to make the model. So usually I just put a comment there as well. Mark it down, put it as a second heading. And here's what we want to do. We're going to start out, of course, by newing up our convolutional neural network, but we just start out doing what we always do and just do keras.models.sequential. Okay, and that basically makes our new model. Okay, so here is what's going to happen. We are going to start by adding one convolutional layer with 32 filters. And again, you might say, well, how do you know to make 32? I'm just picking that somewhat arbitrarily. I think that we can get this to work with much less, but I'm starting out with 32 now. Each of them is going to be 3 by 3. Okay, so we have a 3 by 3 window, which is this little dotted line here, and we're going to convolve this across here, and we're going to get a 26 by 26 output because we always we can't really center this box over a corner because it would be outside the range of this image. Okay, so we're going to lose some pixels there. Okay, so there are going to be 32 of these, and we're going to get an output there like such. So I'll put a little comment here. This is just saying that we're putting in a convolutional layer with 32 filters. Each is going to be 3 by 3. And then here's that little note about losing some pixels here due to the border. Okay. We can manually shape it to be 28 by 28, but here's what we're going to do. We're going to do, again, to add a layer, we're always going to do model.add, and we're going to use the same prefix here, tf.keras.layers. Instead of doing a fully connected layer or a dense layer, we just do conv2d. Okay, and we'll do 32, 3 by 3. Okay, and then right here we want to put what the activation is. And then we can put down what the input shape is. So this is going to be 28 by 28 by 1. Okay, so we added that layer, and the documentation, I can just put that in a comment here. The documentation, you can just go to the Keras help documents and really just look up convolution 2D, and you'll find it. All right, so now what we want to do is do some max pooling here. So I'm going to show you an overview of what the entire network is going to look like. And then I'm going to show you just how we kind of implement these one at a time. Okay, so the first thing, I guess we can just look at an overview. I guess I could have presented this first, but we have our input. We're going to do a convolutional layer. We're going to do pooling. We're going to do a convolutional layer. Then we're going to do pooling again. And then a convolutional layer. And then a fully connected layer like this. Okay, so we just did the convolutional layer right there. What we're going to do next is do the pooling layer, and the pooling layer is going to be implemented like this. Apply a max pooling layer 2 by 2. The stride is also going to be 2. And that will be the default, but I'll show you how to change it in case you want to make it different. So to do the pooling layer, we're going to, whoops, my fingers are off. We're going to do model.add tf.keras.layers. dot, pretty simple, max pooling layer. I'm sorry, max pooling 2D. Okay, so what we're going to do here is we're going to add a pull, we're going to specify a pull size to be 2 by 2. Strides, we're going to set that to be 2 by 2, but this is an optional parameter. Okay. And again, if you want the documentation for this, I'll paste it right here. Okay, so you can just go to Keras and look for max pooling 2D if you want, and you'll be able to find it. All right, so the next thing we want to add, if we refer back to our picture, is we want to add another convolutional layer. This time it's going to be 64 filters. Okay, so it's just like this one, except we're going to do 64 filters. Okay, and then we're going to max pull that one. So really you can just copy and paste this right here. All right, and that's going to add that layer. All right, and then let's see, we want to do one more convolutional layer. So I just copied and pasted this one, 64, and I broke it. So let me fix it. Okay, so we're good now. I probably ran one of these twice. All right, so at this point, we have the output of a convolutional layer, which would be essentially a bunch of filtered images. So 64 filtered images, each 3 by 3. Okay, so what we would want to do is flatten this out so we can add another layer that basically gets those images that are filtered and creates a single dimensional input. Okay, so we would have let's see, this would be layers dot flatten, like this. Okay, and this is just flattening is their word. I use unwrap rows into a single row, I guess. Okay, so there we have that. All right, so you could build this and look at the summary if you want. Okay, and that's done with just typing model.summary. So just to make sure I didn't do anything twice, we have a convolutional layer, max pooling, convolutional, max pooling, convolutional, flattened. Okay, so that looks okay so far. So what we want to do next is add our fully connected layer, or dense layers. So let's just, oops, this should be markup. Sorry, markdown. And we're going to take this flattened layer as the input into the dense layer here. So we want to do tf.keras.layers.dense. All right, and I can refer you back to this image again, and what we'll have is this. Okay, we'll have a dense layer of 64 right here, and then we'll do a dense layer of 10. So the fully connected layer is pretty small, but it does have quite a bit of inputs. Okay, there's 576 inputs because that's what we get when we have all these filters. All these filtered images unwrapped and inputted into this dense layer here. So we'll go ahead and add this dense layer And what I need to do, I do need to specify how many we want here. So we're going to do 64. And for this, we're going to do ReLU again. So this would be a layer right there. Okay. And then what we can do now is add our output layer. And again, we might find that this fully connected part needs more layers. It could need more neurons in each layer. But again, this one should work pretty well. So this would be the output layer we're adding now. So it's btf.keras.layers.dense. Okay, so we have digits 0 through 9, so we only have 10 classifications. Okay, so our activation for our last layer should be softmax here. So this is our output layer 0 to 9. All right, so let's look at our model now at this point and make sure I didn't screw anything up. So we have convolutional, then a max pulling convolutional, max pulling convolutional, then we flatten it, then we have a dense layer, and then we have our output layer. Okay, so there are 93,000 weights in here, weights / filter values. Okay, so really we have weights and biases in the dense layer, and then we have just the filter values in the convolutional layer. All right, so the next thing to do, we can compile this. Our optimizer, we're going to use a different one this time. RMS prop. Now this is a different optimizer than what we've been using, Atom. So what I can do is show you this documentation here. So I have the documentation for Atom and RMS prop. They are slightly different. What I like in the documentation is it says, you know, what the gist is. All right, so it says maintain a moving average, divide the gradient by the root of this average. So RMS stands for root mean square, first of all. So it just uses a slightly different type of momentum. Okay, so here is Atom, and basically what I find that people do is if they have a very small connected layer, dense layers, I do see RMS prop being used sometimes for that. So since we only have one layer, I'm using RMS prop. We could try it with Atom as well. The results might even come out the same. They might come out better. Okay, so the loss function is categorical. And again, metrics, as I always say, don't forget that's a list. So you do have to make sure you put a list of one or more items in there. Oops, I screwed something up. Always forget the equal sign. Okay. All right, so now we're to the point where we want to try to train this model. And as a sanity check, I'm just going to print this out again just to make sure I didn't accidentally add anything. Okay, good. So I can get rid of that. So I am on a GPU now, but I don't know how long this will take. I am on PIT system with an A100. So we would want train labels. Let's try 5 for epochs. 64 will do for the batch size. And let's see how long this takes. If it takes a long time, I'll just pause it and let you know. But let's see what it does. Hey, it errors. It's exactly what I wanted. So this should be, I haven't set it. I said epochs, but I wrote epoch. Okay, so let's see what's wrong here now. Okay, so there we go. I had a typo there. So make sure that you don't do the same thing that I did. Okay, so I had accuracy spelled wrong. I had it like, let's see. I had it like this. Okay, you can see the little error there. Okay. I had archy. Oops. So make sure you do it right. All right, so this is running. First epoch, we're at 94. That's pretty good. All right, so this thing is about finishing up. Took roughly 3 minutes, 36 seconds per epoch. So now let's see how well it did. So we can do it lots of ways. We can test random items like we did before, but I'm just going to go ahead and do an evaluate. And we want to go ahead and use our test labels in this one. And we are 98-ish%. Okay, almost 99. So that's pretty good. Once again, if you want to save your model and not have to go through this whole thing again, you can go ahead and save it. We just did model .save, and then just give it a name. I'll just call it CNN model. Okay, and it should make an image. I'm sorry, it should make a file up there. We do get that warning about something being deprecated. I don't know what that is. But if it works, this will show another file right up here. Okay. Okay, the next thing, let's see, and that's fine. Let me go ahead and I like to read it in just so I have a starting point to, in case you want to come back to this. So I call it model.readIn. Okay, so we'll do keras.models.load model. And then, again, whatever you just put up there. Oops, dot model. Okay, so it read it in okay. And just in case I accidentally run everything again, I would comment this out because it takes a while, and I would make it so I don't actually accidentally save a bad one. I've done that before where I've commented this out, but I had a save still in there. And basically what you get is an untrained model, and it's not good. You just have random values in there, so it's pretty bad. Okay, I could show you that, but it's probably more fun if you learned it on your own. All right, so we can do this. We can just make a list of the predictions, and we can use this thing, the model read in dot predict, and then we'll just take the test data. Okay, and if you want, you can print that out like that, but again, it's not very user friendly. Okay, because this is showing This is showing the raw neural net output, and that doesn't really help us too much here. So what we can do is just do what we did before with the other example, and we'll do print. We'll do the argmax, which is going to get the max value, right? So it's for winner take all. Oh gosh, I have to hurry because my family's coming home and they're going to make a ton of noise. All right, so let's see. I did 105, so it thinks that's a 9. I have no idea. We have to plot it and see if this really is a 9. Okay, so we'd want to print the test images sub, what I pick, 105. And good, that looks like a 9 to me. All right, so one of the things we really, really want to do with this is visualize the filters. So to do that, we would want to do this. What we want to do is graph what it looks like when we pass an image, like this image, through a trained filter. Okay. So for example, we want to maybe take this 3 and pass it through one of these filters and see what it looks like after it's filtered. We would also want to look at what these filters all look like. What do these 3x3 filters look like? Okay, so we're going to look at some of the visualizations of each of these. So our network consists of an array of matrices. So our model has an array of matrices. And what we want to do is visualize these. All right, so probably what I would do is just copy this into a variable, maybe just called all layers. And what I'm going to do is I'm going to copy all of the layers into there. All right, so you'll see if you just display this like such, it just doesn't really tell you much. It doesn't dereference any of these things. But in any case, we can at least see what the types are of each of these. So there's the convolutional layer, and then the pulling, so forth, all the way down to the dense layer. What we can do is even just look at one of the layers. Maybe just the first one, like this. And of course, we can just verify that it's convolutional. Okay. So to get this in a little bit better form, what we want to do is just get the weights, okay, or the filter values essentially. So I'm going to say filters and biases are going to equal to all of the layers 0. So we're going to get all the stuff from the first layer. Specifically, we're going to get the weights. So this would be the filter values here. All right, and then if you just want to look at the filter values, essentially this is the values of the trained filters. Okay, so these are the weights, okay, which are essentially the filter values, okay, for each of the pixels. Okay, so this is what the first one looks like, second one, so forth. Okay, the next one, let's do this. So essentially these values that you see are going to be the values of each of these matrices here. So printing, we see this. What you can also do is just print the shape of this as a sanity check here. And you can see that we have a 3x3 filter of a monochrome value. Okay, so only one color value. And then we have 32 of them in the first layer. And this represents all of the weights that we have, right? So this would be the actual weight values. So what we need to do next is make an instance of a plot. And I can just call it figure 1. And we'll set it to something like plot.figure. And what you need to do is set the dimensions of the figure here. And we have quite a bit of them to plot here, so we'll make them kind of small. We'll make it, let's see, this is going to be fig size in here. Okay, so that creates a new one. And you could just print it now, but what's going to happen is we need to make a bunch of these. So we have 32 filters to print. So we got to kind of figure out how many we want, how many rows we want, and how many columns we want. So I'm just going to do 6 columns and 6 rows. And that would give us 36, but maybe the bottom one, we only have 32 total. So the bottom one will just have 2 in it. So we have 32 filters, right? So I'll just make a variable because we're going to need that too. So what we have to do is make a loop. And we're going to use a little bit of Python syntax candy here. All right, so to make a loop, that's all we do. Make sure you put a colon in, and make sure you are indented with tabs. Don't use spaces. Spaces are not going to work out very well. Okay, so what we're going to do is make our graph here. Oops, let me do this. We're going to say that figure 1 equals plot. We're going to say subplot rows, columns, I. Okay, so if we just do this now, we should get a bunch of empty pictures here, empty plots. And you'll also notice that we have these little tick marks. Our goal is just to print little 3x3 squares with filter values in them. So right now this is a little empty. You can get rid of these little tick marks. All you have to do is just put in some options in here. So we can say, let's see, figure 1. Oops, I need to do this afterwards, after we make it. So right here we want to say figure 1 dot set x ticks. Okay, you can just leave it empty like this. I'll put a comment here. This will get rid of ticks on x-axis. Okay, and then you can do the same thing, except just do it for the y-axis. Right, so there we go with that one. And then you can show this. Now, sometimes I have an a plot.mshow and then sometimes just a plot show. Some IDEs and will put all your plots in a separate window. I'm just doing it in line. Okay, so I'm putting in the mshow here. And what we want to do is this. Oops, sorry. This should be a bracket. Okay. And you can set, well, let me not do this yet. Let me just do it like this first of all. Okay, so by default, I can't remember what color map it uses. I just forget. I don't know. So for something like this, the color map gray is going to, it's probably going to be the best, right? So make sure you use gray, and if you do gray, it doesn't like gray spelled like that. It likes it spelled like that. Okay, so that's the type for that one. And then you can put this in here if you had another window that is collecting your output plots. All right, so how do we interpret this? Well, first of all, a white box is a high value in the filter. Whoops. And black, black would be a low value. Okay, so these are the filters in the first layer. And you can interpret these. We can look at this and say, oh, this one's detecting a corner, like a bottom left corner or bottom left edge, whatever you want to call it. This one here looks like it's detecting a bottom edge. Okay. This one looks like it's getting like a middle edge or almost like a T. Okay. And what we want to do, we want to see what an image looks like when it is passed through these filters. So we want to take maybe one of the original images like this 9, and then we want to go ahead and pass it through these filters and see what the output looks like. So what we need to do is kind of grab hold of the convolutional layers. So if we look at, let's see, I need to find our summary here. Okay, so if we look at this, we see that we have a convolutional layer here. Now remember, this is just an array, right? The model is just an array of layers, right? So we did basically added a bunch of layers into here. So the first one we added was right here, right? So we have a convolutional layer at index 0, 1, 2, and 4. So 0, 2, and 4. Okay, so this is interesting. What we want to do is just see what the image looks like going through the convolutional layers without these poolings, okay, and without the the dense layer and the flattened layer. So what we're going to do is we're just going to make another model, and we're just going to copy these things into it. All right, that's all we're going to do. So what I do, probably the easiest way is just to make an array of the indices, right? So we said, we said that the convolutional layer indices are 0, 2, and 4. Okay. And what we're going to do is we're going to do this. We're just going to copy this. We're going to do this. We're going to say model.layers sub I. All right, this is, again, some syntax candy here. You could certainly write this in a separate loop if you want. Output. Okay. This is just like another trick. Dot output. Okay. Then we can just make a little for loop after. Okay. So what's this doing? This is just pick out all of the convolutional layers and store them in this thing called output. And it doesn't work. So let me fix that here. Okay, so I have to make sure that these are called the same thing here. So it looks like I have an invalid symbol. Right, so you can see here I called it conv layers, and this is just conv layer. So I'll make that consistent. And let me call it outputs as well. Okay, so there we have that. Now I could just print the outputs, right? And we can see that these are indeed convolutional layers, right? Right here. Right, so if one of these had dense or you know, one of the max pulling layers or something like that, then we know it would be wrong. Okay, so that looks okay. So what I'm going to do, this is just a copy of the layers. This isn't really a model. This is just an array of 3 layers, and they're not really associated to a model. So we can make a new one. I'm going to call it model shortened or something. And we'll make a new one. Oh. Okay, so we have this, and we'll say model. I'm sorry, we're going to set the inputs to be the same thing as the model inputs. So we'll just copy the inputs layers over here. Okay, and then the parameter here, we can say outputs equals, actually I called it outputs. Okay, so if we show this one, actually we need to do a summary. So just go ahead and print a summary for this one. All right, and let's see. Now, okay, you see we don't have any parameters in these here. Okay, so comparing it to the original one up here, you can see we have 93,000 parameters, and then of course we have the dense layers in there. And then the one we just did, we have 55,000 parameters, and we don't have any dense layers. All right, so I'm going to just paste some code in here. You might want to pause the video and just copy it in. But I can show you what's going on with this. Okay, I just have rows and columns being 6 by 6 so that we can, again, look at all of them. So this would make 36, but we only have 32 filters, so that's fine. Now this thing. This is going to be the index of the number I'm going to try. So the index of 12 happens to be a 9. But that's just what I'm trying right now. So I'm just grabbing this one, which is just an image of a 9. The next part is going to expand the shape, okay, of this now of the test images. So what I'm going to do first, I'm going to display test image dot shape to show you what this does. And let me just get rid of this for now. And then I'm going to show you the next one here. And now after we expand it, I'm going to show you what the shape is here. Okay, so fix that and put a print statement around that. And then put a print statement around this one again too. Okay, so we can see what it does. It just adds a dimension to this here. So I can go ahead and put this code back in there. I just wanted to show you what expanding does. Now, if you remember before, I made a copy of the test images, okay, because this is the one before it's flattened, okay. So I did that so we can still print these later on. So if we just look at this one, you're going to see that index 12 is the number 9. I mean, I can try a different one. I can do, 18 or whatever. But I'm just doing 12 for now. Okay. Okay, so what are we doing here? Well, I'm going to use that smaller model to basically push the image through the filters, okay? And predict is just going to do a feed forward, okay? And what I'm going to do is just plot the output of this number 9 through all of these filters. And it's going to look like this. So this is what it looks like through the filters. And we can kind of look at some of the patterns here. Okay, so a couple things. You can see that this filter seems to be detecting top and bottom edges of the loop part. Okay. This one seems to be concerned with the top and bottom of the loop as well. Let's see, what other ones do we see? Now, again, I never know what these are going to look like every time I train it, right? Because these filters are trained and it can definitely vary. Okay, this one is interesting over here. It seems to be trying to detect the line of the 9 and the left part of the loop. Okay, so sometimes these are hard to interpret. They're not supposed to be 100% obvious to us. We might think we know how to make some filters, but again, this one here might contain some secret sauce to make the whole classification work. Okay, so looking at the next one, okay, you can see that that this is shrunk, and we can look at some of the patterns of the second one after it's been pulled down here. And let's see, it looks like this one is trying to detect the straight line. Okay, so we can maybe pick another number that also has a straight line in it. Okay, so we can look at, let's see, I wrote offline here, I wrote a couple comments on which of these indices are which. So here's just a couple. If you want a 0, you can pick index 3, 10, or 13, right? So if I pick 3, I know that's a 0. If I pick 10, I know that's a 0, right? Okay, and if we take, for instance, let's just say the fourth one down on these bigger ones here, 1, 2, 3, 4. It looks like it's detecting left and right edges of a 0. So let's put a number 1 through here and see how it reacts. So a number 1, oh great. Stand by, have to restart my server. I thought it'd be nice for you to experience some of the pain in making these videos. So as we patiently wait for this to restart, so I think it's useful for you guys to see why you would want to maybe save your model sometimes. The models I'm sorry, the server is going to shut down every so often. I request it to stay on for 3 hours or something like that. You can say I just started it. Now I have to run everything all again to get all my data in memory. But of course, I don't want to train this thing again and wait another several minutes. So what I'm going to do is just make sure that my save is not saving. Right, so find the part where I save it, it's not saving, and then make sure I'm not training it as well. And then I'm just going to run everything again. We would also want to make sure that when you read the model in, that you copy it over to your old model. So remember, we end up using, this variable model down below to go ahead and read in everything. So certainly you could just put, model right there. It'd be fine. So in any case, once we had that, now we get everything back the way it was. And what I did is I put a number 1 in here. It happens to be example 2. Okay. So example 2 is an image of a 1. And we were looking at, I believe, the 4th one down on the side. And you can see that it detects a line here. But of course, it doesn't have that little dot that we saw over there on the 9. Okay. So looking at the filter, we would see right here that it definitely looks like it has some sort of edge detection on a vertical line right here, favoring the left edge. Okay, so you can see that this edge is dark and then these two are light. All right, so when we scroll down to the images here at the bottom, this would be our final filter. We look at the 4th one down again. We have somewhat of a vertical line, and the vertical line, in the 9 is in the middle of the image. However, when it gets max pulled down, it just ends up over here on the right side. That concludes our topic on convolutional networks here. You can see that with a convolutional network, we're going to definitely get some advantages when we start dealing with very large images.